Okay. All right. So we're going to do the part of the higher order derivatives for implicit differentiation today. So what we can, a derivative gives us the slope of the tangent line, or we could think of that as like the rate of change of the graph at that point. So you can continue to take the derivative over and over and over again. So you can take a second derivative and a third derivative and a fourth derivative and so on. For example, if your first original equation is position, then we've already learned that if we take the derivative once, that is going to give us velocity. That's our rate of change, right? If we take the derivative again, it's the rate of change of the rate of change. It's acceleration at that point. We are going to learn how to take a second derivative. Today we're really just looking at like the mechanics of taking a second derivative for implicit differentiation. We won't be looking at the application sort of problems until we get to the second part of these notes. So, for your notation, for your first derivative, there are several different ways that you can notate that you have taken a first derivative. If your original function is called f of x, you can call it f prime of x. For that notation, if you take a second derivative, you just put two little tick marks here. This would be your second derivative of f of x. Or if you're using y prime, I don't use that one very much, but you could. When you take the derivative of y equals something, you could have a y prime. You would just have y double prime with the two little tick marks for the second derivative. And then the last one, we've been using dy dx, specifically with our implicit differentiation for sure. This one is the weirdest on the notation for the second derivative. It is d squared y over dx squared. Okay, to help you think about where that comes from a little bit, let me use a different color over here. To take the derivative of the derivative, we've used this notation before. To take the derivative, we would write d over dx and then have the bracket. So if we're taking the derivative of the derivative, then notice you have like two d's here and your y, and then the dx squared. Technically, you would need parentheses around that dx, but I guess that's more cumbersome than they wanted for the notation. So this is what you would use for that second derivative. Most of the time it's going to be in the problem, so you don't really have to worry too much about where those squares are at, but this is why it is the way it is. So let's look at finding a second derivative. In order to find the second derivative, you must first find the first derivative. Notice here it says give your answer in terms of x and y. Okay, that means you cannot leave like a dy dx or something like that in your answer, other than at the beginning where it's equal to. So we've got to find the first derivative for this. So Ethan, if I'm going to take the derivative of this one here, what will I get?
2x plus 1 plus 6xy equals 0. Or 6y equals 0.
Okay, you're close, but I've left some spaces. Because when you take the derivative of something with a y, what do you have to put with it? You got to put your dy dx. So both of these right here need a dy dx. Okay, Tyler, what are we going to do next? Good. Good. Is it all right with you guys if I go ahead and factor out that dy dx in this step 2 of 1 plus 6y? That'll save me a step if I do that. Okay, and then Solana, what's the last thing we'd have to do here?
You divide by the
Very good. Okay, so we've got dy dx equals negative 2x over 1 plus 6y. Very important that you get that derivative right before you go on to the next part, because if you miss this, obviously you'll miss the next part as well. So that's just our first derivative. Any questions there? All right, now we need to take the second derivative. What have we got to use to take the second derivative? We've got to use quotient rule. So Joshua, if I use quotient rule to take that second derivative, I'll have d squared y dx squared equals. What will I get whenever I take that derivative? Beautiful. I like that he did not forget that dy dx. It still holds whenever you take the derivative of something with a y, you have to put dy dx with it. Okay? So, let's clean this up a little bit before we go a little bit further with this. So, let's distribute that negative 2. We'll get negative 2 minus 12. Y, and then this will become plus 12x dy dx over 1 plus 6y squared. Now, the problem said that we had to leave it in terms of x and y, which means that we can't have a dy dx in our answer for this. Any ideas about what we should do? You could, but it would not get you anywhere because it wouldn't like cancel with this one. You'd just end up with more dy's in the top and a dy in the bottom. So you could do that, but it wouldn't get you anywhere. Well, we don't, because you've got this second derivative here, and that's what you're trying to find. You're trying to find that second derivative. So it's already like solved by itself. So you don't want to move it, or you don't move anything over there with it, because like if we solve for dy dx, then we would not have d squared y over dx squared.
So we like
That's
multiply it by dy dx over dy dx or something?
That won't help us on this one. What is dy dx? We found the first derivative for this problem, right? So we're going to take this right here and we're going to plug it in right here, which, not bad, but it's going to cause us to have a complex fraction, right? So if it's a free response question, it's not that big a deal, because all you have to do if it's a free response question is do negative 2 minus 12y plus 12x times negative 2x over 1 plus 6y over 1 plus 6y squared. So on a free response question, on FRQ, you would stop here. You wouldn't necessarily have to go any further than that right there. Everything's in terms of x and y. It's a mess, but it's in terms of x and y. So you would stop. However, if it is a multiple choice question, there is almost no chance that they're going to leave the answer like this. So, you've got some different options on how to deal with it. You only have just this like one thing that's in the denominator, right? So the first thing I would probably do is I would combine this together. So this is over 1. So if we wanted to write this way, we'd have negative 2 minus 12y. And then we would get minus 24x squared over 1 plus 6y. Okay, so I'm multiplying the 12x by the negative 2x to get that 24x squared, put the minus out front. And then the bottom 1 times 1 plus 6y is this. Okay, over 1 plus 6y squared. And it is tempting to like say, well, maybe we can just pull this one down here with that, but we cannot because it doesn't go with every term, right? So what we want to do for this one, if I need to get rid of a denominator, I can multiply through by that denominator. Okay, so I can take the numerator and I'm going to multiply by 1 plus 6y. But if I multiply the numerator by 1 plus 6y, what must I do to the bottom? Same thing, 1 plus 6y. In the bottom, this will be fairly simple because you have 1 plus 6y to the first power times 1 plus 6y to the second power. You're just going to combine those and you'll get 1 plus 6y to the third power. I'm going to go ahead and do that. In the top, you are taking this whole thing and you're distributing. Unless you're really good, I would write it like this. Right? You're multiplying it by negative 2. Then you got a minus 12y times 1 plus 6y. And then you multiply it by the last term. What's going to happen when you multiply 1 plus, actually I'm going to just do it here. So we got minus 24x squared over 1 plus 6y times 1 plus 6y, like this. Okay, the reason that we do that is because that 1 plus 6y is like 1 plus 6y over 1, right? And now those denominators will cancel. Or that denominator will cancel. Are we okay there? I think that's the trickiest step of this. So what should we do now? Let's distribute. So we will get negative 2 minus 12y. Here we'll get negative 12y minus 18y squared. And then since our denominator canceled there, we've just got minus 24x squared. That's a good question. I guess I added those together. So there, we're going to do 12 times 6, so we'll get 72. Does that look better? And then we'll have 1 plus 6y to the third. And then the only real thing that we've got that we can combine are the 12y's. Those can combine there. What they'll probably do here, since everything in the top is negative, they will probably take a negative and put it out front and will make everything on top positive. They'll also probably put this like in order, maybe something like this, 24x squared plus 72y squared plus 24y plus 2. I guess there's also a chance they might pull out a GCF there. Just take that 2 out. It really doesn't help you do much there, so I'm not going to mess with that right now. When you pull out the negative, it can go in the top, it can go in the bottom, or it can go out front, but you would not want to do both because a negative over negative would make a positive for that. So you could like put parentheses in the top and just keep the negative in the top. That'd be fine. But what they usually do is like pull it out in front of the whole fraction. And so something of this nature is probably what you'd see on a multiple choice question. Okay. You can see these are a little bit tedious because usually, especially if the first derivative is hard to get, then the second is really going to be bad. But it's the same process we've been doing. Mm-hmm.
So what is that second derivative like representing? I know you like talk about it.
Yeah, it is your rate of change of your rate of change. So it like for me thinking about velocity helps the most. So like if you look at a first derivative, that is your velocity. Like if you're driving down the road, it's how fast you're going. If you take the second derivative, it is the rate of change of your velocity, which is your acceleration. If you were going, like if your velocity is increasing, then you're speeding up. Your acceleration would be positive. If your velocity is decreasing, if you're slowing down, then your acceleration would be negative in that case. Yep.
So if your first derivative gave you miles per hour, does this give you miles per hour per hour?
Yes.
Is that what you're looking at?
Yes. And if you did a third derivative, it'd give you miles per hour per hour per hour. Although that is not as useful in actual application as miles per hour per hour. Here. And then this could also apply not only to like position, but if you are making lots of money. And so like your original equation would be like the amount of money in your bank account. Your derivative is the change in your bank account. So are you earning $1 million per year, or are you earning $7 million per year? Then if you take the derivative of that, it would be like your money per year. So that would be like over time, is this like accelerating and going up, or is it evening out? It'll apply in those situations. So, and we'll talk more about those applications later. Right now we're just going through the process of it. Okay? All right. How about everybody find the first derivative for this one for me? So that one should be something we should be able to do fairly well. Go ahead and find that first derivative. You must use a product rule for this first part. It's easy to miss because it's so little. Like it doesn't very obviously show up as something with a product rule. But you've got to I let 3x be my f of x, and I let y be my g of x. You also could just keep like the 3 out front and distribute it later. So you got to do 3x times the derivative of y, which is your dy dx, plus y times the derivative of 3x, which is 3. And then the other parts, you just take the derivative of like you normally would. You'll get 4x right here, and you'll get 10 here, but it needs a dy dx with it. And so you got to take 10 over here to the left side. You're going to move these two pieces over to the right side. Factor out your dy dx, and then divide by that 3x minus 10. So I got negative 3y minus 4x over 3x minus 10. You could factor out the negative. You could have negative 4x minus 3y. That'd be fine. There's a few different ways you can make it look in the end, as long as it's equivalent. Okay, questions on that part? Okay, so we want to make sure we got that right first. Then we go on to second derivative. So when we take the second derivative, we will have 3x minus 10 times the derivative of negative 3y minus 4x. So we're going to have negative 3 dy dx minus 4. Make sure you've got parentheses around that.
Why is it negative 3?
We're taking the derivative of that top part.
I didn't see the negative.
Minus negative 3y minus 4x times the derivative of 3x minus 10. That's just going to be 3 over 3x minus 10 squared. Now, if we were doing this problem for FRQ, we would not be done yet, but we could go ahead and just like plug in for dy dx and leave it like it is. And there will be times where you see problems like this, and that's what you want to do. You don't want to try to like do any crazy simplification. But in this case, I probably would distribute here first and try to simplify anything I can before I worry about that dy dx. Because if you plug in the dy dx right now, actually, I don't know. I might change my mind on that. If we go ahead and plug in our dy dx right now. Let's just do this, okay? Here's why I want to change my mind on that. Okay, here's why I decided to change my mind on that. I need to distribute this 3x and the 10 over here. So I could do like the FOIL method. Or you can think of it this way, where you're taking this whole thing and you're multiplying it here and here. Right? So if you do that, I'm going to write out every step. You would have, I'm going to put negative 3 first, times 3x minus 10, times negative 3y minus 4x over 3x minus 10. So I'm taking this stuff, which is found here and here, and I'm multiplying it by this, right? Then I have to distribute to that negative 4. So that will look like this, minus 4 times 3x minus 10. And then you want to copy down that last part, 3 times negative 3y minus 4x. You could go ahead and distribute. I'm just holding off on that. And so right here, I've got the 3x minus 10 multiplied by that pink part right there, right? So I just took this green stuff and I distributed it to the yellow stuff and to the pink stuff right there. So the reason that I decided to do it this way is because when you do this, this stuff right here does not have a denominator, so it's in the top of the fraction, right? What can happen right here with this 3x minus 10 and this 3x minus 10? They will cancel out. Okay, so really you're just left with this negative 3 that needs to be distributed. So you got 9y plus 12x. You'll distribute your negative 4 here. You'll get negative 12x plus 40. And you'll distribute this negative 3 plus 9y plus 12x. Excuse me. Almost made it to the end here. Now we just want to simplify. Anything we can simplify. You could cancel out that positive 12x and the negative 12x. You could put the two 9y's together. You'll get 18y plus 12x plus 40 over 3x minus 10 squared. You could factor a GCF out at the top by like dividing those by 2 or something, but it won't cancel with anything in the bottom, so we'll just leave it here. So you can see these problems, let's zoom back out, they're not your easiest ones, because there's going to be a lot of simplifying and stuff that goes on. All right, let's go to this last one. So I find these a little bit easier if you're actually plugging in a value. Now, this one is trig, which may not be something that you find necessarily easy. But if you're actually plugging in a value, it makes that last step where you got to plug in a little bit easier. So here they're asking us to find the second derivative. What's this line right here mean? Such that, yeah. So such that xy equals 3 over pi, comma pi, right? So that point, right? So we got to take the derivative here. How do I take the derivative of xy? Product rule. And I can't tell you the number of kids that do it wrong because xy is so little it feels like it doesn't need any special rule, but it does. So you've got to do x times dy dx plus y times the derivative of x, which is just 1. You don't have to write that if you don't want to. And then I'm taking the derivative of 3 cosine y. That does not need a product rule because you don't have an x with that 3. What's the derivative of cosine? Negative sign. So I'm going to have minus 3 sine y. Since I took the derivative of something with a y, I must multiply it by dy dx, and that is going to equal 0. So over here on the left-hand side, I'm going to go ahead and factor out my dy dx because everything's already over here. I've got an x and a minus 3 sine y, and I'm going to move this y over here to the other side, so I'll have a negative y there. Very good here. Last step for that's to divide. So okay, questions? All right, second derivative. We are going to have to use a quotient rule here. So we got d squared y over dx squared equals, all right, we'll have x minus 3 sine y times the derivative of y, of negative y, which is negative 1. And what has to go with it? Dy dx minus negative y times the derivative of x minus 3 sine y. Derivative of x is just 1. The derivative of sine is cosine, so we're going to get 3 cosine y. And since we just took the derivative of something with a y, we need to do dy dx there. And then all of this will be over x minus 3 sine y. Squared, thank you. Alright, so we can, like, our next step could be to take this stuff and plug it in here. But I don't even want, you got two different places with a dy dx. And I really don't even want to think about having to deal with all of the derivatives and the different places and the fractions and the trig and all of that. So here's another option. For this problem, they are asking you to plug in 3 over pi, right? So we could just go ahead and plug in 3 over pi and pi. So our notation here looks like this. D squared y over dx squared. Our line for our such that x, y equals 3 over pi. Pi is the right point, isn't it? Yeah. Okay, and we are just going to plug in the x and the y coordinates for most everything. So for my x, I've got 3 over pi minus 3 sine of pi times negative 1. Now, for dy dx, I've got, I'm going to do this for right now. I'm going to call this dy dx such that xy equals 3 over pi. Fix that. Okay, so I could plug, this is my derivative with those values plugged in. And then right here where I've got that minus, I'm going to make that positive. So plus my y is pi times 1 minus 3 cosine of y, which is pi, times the derivative with in all over 3 over pi minus 3 sine of pi squared. Did I plug everything in right? I mix up an x and a y. I do that so often. We're good. Okay, so what I can do up here is I can go up here to dy dx and I can plug in 3 over pi. I need to put parentheses there. So I would have negative pi over 3 over pi minus 3 sine of pi. What is sine of pi? It is 0. So that is going to be negative pi over 3 over pi. And how do we divide fractions? Easy as pie. Flip the second and multiply. So that's going to be pi over 3. And that will give me negative pi squared over 3. So this can go in both of these spots right here. So it's still going to be like a terrible mess, but we got 3 over pi. What is sine of pi? Is 0. So that's just going to be 0. It's going to go away. We're multiplying that by negative 1. We're multiplying that by negative pi squared over 3. Plus, we got pi times 1 minus, what's cosine of pi? Almost negative 1. So that's going to make that a positive 3 right there. And that's going to be multiplied by negative pi squared over 3. And then in the bottom, we will have 3 over pi. And this is going to be sine of pi is 0 again here. So that'll be 0 and that'll be squared. And you guys need to go to Miss Mullis. So we are just going to pretend that this is a free response question where we could stop right here. Because on a free response question, you definitely would not want to go any further than that. You would have to show the step where you plug this in, but you wouldn't want to go any further. So we'll pretend that's the case.